gallery view, you could put it on speaker view, and then you could, up in the corner, just tap speaker view and bring it back to gallery view later. But if you tap it on speaker view, then Karen, go ahead and say something, and then Karen's book will show, the book will show
so I'm
up.
holding the book up. I have this background, and it keeps picking up the book as the background. If I get rid of the background, I can hold it closer probably. But this is what the book looks like. It's a hardback book. It's very nice with this sort of glossy, shiny cover, and has a lot of beautiful illustrations that we didn't do, but really illustrate the book very nicely. So it's been nice to be part of.
Oh, It's a wonderful program. See, the 30-second series is produced by a press in the UK called Ivy Press. And they have 30-second physics, 30-second chemistry, 30-second philosophy, 30-second modern art, things like that. And so they have many topics that are covered in a way that is relatively short and brief, has biographies, has brief information about all the topics, and sort of covers it all so that it's not intimidating at all. It's a beautiful little volume, and it has lots and lots of topics, so you brief through them. Now, the unfortunate thing for us is that it has not yet been published in the United States version. It is a UK product, and it is possible to obtain it through various online booksellers and so forth. However, Barnes & Noble Company actually has the rights to publish the United States edition. And they were gonna do it, and then there was this thing called SARS-CoV-2 that showed up. So a lot of things have not yet made it back over here. But it is possible to obtain it, and it's small, it's very pleasant, and it's good for all ages. At least we wrote it that way in this case. And so everyone, thank you so much for coming. I wanted to let you know that today, unlike most author talks where you have one panel person and one host, you get 3 talks in one, 3 authors for the price of one today. Our plan is to do the following. We have until about 8 o'clock today. And I will be sort of the moderator person and ask Karen questions. And then Karen will become the moderator about 10 minutes after that and ask Sevil questions. And then Sevil will become moderator 10 minutes after that and then ask me questions. And then we'll open it up to general questions for anything you want to ask about in terms of whether it's the astronomy universe stuff or the microscopic universe, the quantum universe, or even a little bit about metaphysics and multiverses, which is what that book contains. A little bit of thought about all kinds of the universe, not just astronomy, not just planets and stars, but think about the whole shebang all at once. So with that, if there are no further questions, let me say that if you have anything you want to ask right away or say anything, type it into the chat, okay? The chat, just tap the chat button at the bottom of your screen or the side of your screen, depending on what you're using, and then just type it in to everyone and we'll all see it. And as appropriate, we'll answer at that point. And then at the end of the talk, if you have any other questions, specifically then, you can address them to individuals or you can do it to everyone and just say stuff. And that's how we'll do the questions and answers in all likelihood. All right. If there are any other questions, anyone wave their hand real quick. I'm just leafing through, see if anybody can see anything. I think we're all right. Let us get going. It is my pleasure to introduce a little bit more my friend, my colleague, Karen Masters. Professor Masters, as you heard Maurice say, is at Haverford College in Philadelphia, but actually your professional path is quite significant. You've been a little bit everywhere, haven't you, Karen? And let me just start by asking you to tell us a little bit about this Sloan Digital Sky Survey thing that you are one of the leaders of. And you know, one of the, I would call, of course I'm biased because I do work with the Sloan Digital Sky Survey also, but I have to say, I think that it's probably the leading international collaboration of ground-based astronomy anywhere in the world right now. Can you tell us a little bit about that and the work that you do about it and you know, how you've sort of gotten to that point?
Well, so the Sloan Digital Sky Survey, I don't know if I'd call it the leading ground-based collaboration today, but it certainly was at the forefront of this way of doing astronomy, which is grouping together in very large collaborations. We have professional observers at our telescopes in New Mexico and Chile. And, you know, we collaborate actually across the entire world. We have members in China, Chile, Europe, even Australia now, as well as the United States. So when I got a job, actually back home in the UK, I worked at the University of Portsmouth for 10 years. And when I moved to Portsmouth, Portsmouth had been a member of this Sloan Digital Sky Survey. And so I started to be involved. And I met Charles when I met Charles through this collaboration. And at the time I met Charles, I was the spokesperson. I still am the spokesperson of this collaboration. And so my job as spokesperson is to kind of deal with the people stuff to some extent. We have sort of like a little council where we have members from each institution, and we get together and we try to make sure that everyone's happy and no one feels that they're being overlooked and all that kind of stuff. We worry about codes of conduct. I also do some of the press type stuff. So sort of as spokesperson, I get involved in helping the collaboration communicate their results to the public. And also I have a job once a year. We put out a data release. We make our data public to everyone. So Sloan, as well as sort of being the forefront of this collaborative way of doing science, has also been at the forefront of open data. Been running for 20 years, and we're now on data release 17 that I'll be working on for next summer. And so I have a job as part of that to kind of coordinate a paper that we put out, and which describes very technically the data that we're putting out. So.
Right. And literally people throughout the world can just log on to the Sloan Digital Sky Survey website and use that world-class data, the data releases you're describing, to do any research they wish, right?
That's right. And people do. We get emails from high school students, from just people who are generally interested, who are using the data. We like to say in Sloan that we don't just make it available, we make it accessible, which means we document it, we provide tutorials, we try to help people make use of it. Perhaps the most famous use of it, certainly from my perspective, because it's something else that's very close to my heart, has been Galaxy Zoo. So Galaxy Zoo is a crowdsourced citizen science project that put images from the Sloan Digital Sky Survey initially on the internet. And millions of people have looked at images from SDSS from the Sloan Digital Sky Survey as a result of Galaxy Zoo. So, yeah.
Wonderful. And Sevil, I know you're getting your own time in a few moments, but I want you to jump in also, because you also do international collaboration with your work, right? And that's absolutely necessary when it comes to the work that you do, because there are only a few facilities in the world. Isn't that right, Sevil?
Yes, that is correct. So I've worked in really large scale international collaborations. For example, one of the accelerator facilities that I work is in between Switzerland and France. It's so big that it actually goes in both countries. And if you, for example, go to the CERN facility, this European nuclear accelerator facility, you can find all sorts of different languages being spoken in the dining halls, for example. Then you see people are collaborating. We need these because, again, these are very expensive and large facilities that requires many different people to collaborate and come up with it financially, and also, brain power together to actually be able to run these large scale facilities. Yeah. I mean, this happens in Europe. This also happens in US, because there's a facility in US too called Relativistic Heavy Ion Collider. And similarly, even though it is based in US, we have collaborators from China, from Germany, from France, and in some Latin American countries. And so, yeah.
It's great. When I read particle physics papers, I'm just amazed at the hundreds and hundreds of people that are involved in every result. It's just amazing how the world can collaborate so well, even though sometimes it feels like that we don't do such a good job of talking to one another, certainly in the scientific world.
Yes, yeah, and I mean, going through the papers discussion, for example, CERN, when we write papers, it has to start from the country, Albania, in the alphabetical order. So, if you want to be the first author, you have to be coming from an institution that starts with an A from a country, Albania, and a last name of A. So, and then it goes in that order, yeah.
That's amazing. Okay, so Karen, back to you a second. This book, as you know, covers a lot of ground, right? And each topic only briefly. In fact, the reason we needed so many authors, 3 people to write this, is because no individual person could probably cover all the topics as an expert in any of it. So how is writing this book, Karen, similar or different to, say, the scientific research that you typically do?
Well, that's a really interesting question. Well, it was very collaborative, right? So we're working together on this, and that's always fun because, you know, Sevil is a high energy experimental physicist, knows a lot about particle physics and the little tiny particles. And Charles and I have more expertise in, you know, astronomy observation and observational cosmology, observational constraints. And so it was really fun to be able to bring those things together to kind of fill out this book. One of the things that's really interesting about science, a lot of people think science is very like you're kind of sitting alone doing your thing. You know, we've kind of presented a very collaborative version of science, but also science, like we spend a lot of time thinking about how to communicate what we do. So trying to explain what we're doing to other people, because otherwise, you know, you're just throwing out a string of acronyms and facilities. Who knows what these things do, right? And so in that way, you know, writing this book was really nice because it was, you know, a different audience to think about and a different way to try to present what we're doing. So
yeah, were you able to tell some stories that you wanted to tell through this book that you otherwise wouldn't be able to, like to say your fellow scientists, you know, we who read the astrophysical journals, anything like that?
Yeah, I mean, so one of the articles I'm most proud of is the one about baryon acoustic oscillations, which is a very technical sounding term. And I was like, what are we doing trying to explain this? Because it's a very technical thing. And, but it was, I had many conversations with a colleague about how to explain this, her research. So this is a colleague from within the Sloan Digital Sky Survey. So apologies if I mispronounced that earlier, but it's the Sloan Foundation is the foundation that helps to pay for it. We'd had conversations about how to explain this this technique, what this is, and it's just sound waves in normal material, and sort of metaphors to use. And so I was really pleased to have a venue to write that down. So that was good.
The Big Bang banging the universe itself like a gong, something like that.
Yeah.
Right? Is that how you were describing
Kind
it?
of like that, right? It's like ripples. And so her metaphor was about, imagine throwing a pebble into a pond and you get those ripples that come out. And now imagine your pond is getting really cold, like really quickly. And so as the ripples kind of move out, they freeze in place. Okay, and now instead of just throwing one pebble, throw lots of pebbles and then freeze it in place. And you've got this crazy pattern, but actually frozen in that crazy pattern are these circles of a certain scale that tell you how long after the pebbles fell in the pond, it froze. And that is not exactly what's going on in the universe, but it's kind of similar actually. And so it's just a really nice metaphor for how we use these like crazy patterns in the distribution of galaxies in the universe, how we can use that to actually put constraints on cosmology.
That's great. So I have about a minute and a half left in my 10-minute block. So here's my last question for now. You and Sevil, I guess, both experienced your early schooling not in America, right? I mean, I spent a year in Taiwan as a student or so, but that's not at all like that because I was really an American product. But what was it like for you, and Sevil, jump in too if you want, like your education in another country, another system, maybe compare and contrast that experience with your own children who are now experiencing the American school system, especially when it comes to things like science and technology.
I don't think there's a huge difference in science and technology. It still slightly astounds me that my children are learning to measure things in feet and inches in 2020. And I'm like, what's going on with that? Because that just seems very old fashioned. We moved away from those measurements in the 1970s in the UK. So I did know about them as a child, but they were like the old way of doing it. But I think the big difference is the history. So I'm learning all kinds of American history. My son started in second grade. My kids actually had a few years of school in the UK, but my son started in second grade in the US, and second grade was all American history. And so we learn all about all different states and all this kind of stuff. So that's kind of fun.
Great. And Sevil, you were in Turkey, is that right?
Yes, yes. So I grew up in Turkey, Istanbul, and then I did this crazy international student transfer to UC Berkeley for my undergraduate degree. So I finished my, university degree in US, but now I actually see more of the differences because, I have a son who's going to be third grade and a, little daughter who's a kindergartner, and then he comes up with some problems and I say, you should have been done with this thing already in the kindergarten level, right? Mm. So he's still trying to learn multiplication. I mean, I think the level of curriculum is much less dense, especially, I mean, as I can see it in the elementary school level. But then I think then by the time that they are done in the high school, by the time that the students are coming into the university, our expectations from those students is much more, so they get their, you know, shock. I mean, in Turkey, we had to go through these nationwide exams in much in every mid-level, so that meant that the students had to be prepared, you know, from elementary school to middle school to high school to university. So, you know, it was a little bit more rigorous in the level of primary education.
Wow, very cool. Okay, let me step aside. Karen and Sevil, take it away.
Yeah, so Sevil, we had a bit of a pre-chat about good questions to ask, and I got to learn a little bit about your job, what you do. So you described yourself as a high-energy experimental physicist who's studying or trying to understand the quark gluon plasma. Now, my astrophysics understanding of the quark gluon plasma is that this is what the universe was like in very, very early stages. And so I wondered if you could describe, you know, the sort of the very beginning of the universe and how weird and exotic and how much it was all to do with particle physics in the very first few moments.
Yeah, so so maybe we step back and then first, before describing quark gluon plasma, we say what are those? So you know, everything that we see around us are made up of atoms. And you know, when I was in elementary school, you know, I was being taught that, oh, okay, an atom is an object that is made up of a nuclei. It's like a seed of a fruit, right? And in that seed, there are protons and neutrons. And then around the seed, there are electrons, and that's what we call an atom. And I think the usage of atom is really interesting because atom means in Greek, the smallest indivisible object. So the expectation was that the fundamental, you know, particles that are made up of all the things that we see are made up of these atoms. But so going into the seed, right, we have these protons and neutrons, so they're actually not indivisibles. There are actually objects that are, you know, compounding to make the atom. What we learned later on is that actually these objects called protons and neutrons are even not fundamental, that they are made up of other things that are called quarks. And physicists not being very creative in naming, we glue these quarks with the objects called gluons to make up a proton or a neutron. So fundamentally, 3 quarks, you know, will be glued to make the proton, and then 3 quarks will glue with the gluons to make the neutrons. So what is really interesting is that if I try to hold the proton and try to pull a quark out of the proton, all the energy that I put into the system to pull this quark, like I try to pull it, by the time that I think that I can separate this one quark from the proton, a quark anti-quark pair pops up from nowhere. And this is this, you know, Einstein's famous energy is equal to mc squared. E, you know, people wear these t-shirts with E is equal to mc squared, energy is equivalent to the mass, right, matter. And that means that you can never study a quark alone in nature. So what we do instead is we try to put a lot of protons and a lot of neutrons in these extreme conditions. That means we, for example, collide heavy ions, and we can come back to that later on too, to sort of compress them so that a quark that belongs to a proton does not necessarily recognize its dress of that it belongs to a proton. And going back to your question of why this is interesting in terms of the big picture, something around 0. And then you put 5 zeros and a 1, right? 10 to the minus 6 seconds after the Big Bang, the universe, it is theorized that the universe was made up of this quark and gluon soup, where no regular matter that we see around now, which eventually later on forms your galaxies and stars and everything, was actually with this soup of quarks and gluons. They were not objects that are, as we see regularly today, as the cold nuclear matter. So in these facilities, we sort of try to make these little big banks, which we call them little banks sometimes as a usage, to sort of study this new novel phase of the matter. So it's like a phase transition. It's like water going into vapor, but we are taking the cold nuclear matter, the matter that we see around us, to really extreme conditions.
Yeah. And you need some pretty extreme equipment to make these mini big bangs, right? And so that's why these facilities are so big and so international.
Exactly. Yeah.
And as an astrophysicist or as an astronomer, I often only hear about them when I hear that people are worried that you're making mini big bangs and that are going to destroy the Earth.
Yes, actually
so
there are different court cases for this.
Yes, so this is not a concern, right? We're not going to destroy the Earth with mini big bangs.
No, yeah. So no, we should not be destroying I mean, and we have been running for example, for Rick for more than 20 years by this point, and we have not yet destroyed the Long Island or New York or US or the whole world. There were some predictions about possibly producing these little tiny black holes, but they're like subatomic particle level. And if you do indeed produce such things, then those will evaporate. So it's not different than any other exotic particle that we study. But yeah, so in these big facilities, so currently relativistic heavy ion collider, which is in the middle of Long Island. So if anybody can still take a flight, right, to Europe, generally speaking, from New York to Europe, sometimes airplanes go through over Long Island. And if you look down in the middle of Long Island, you can actually see the ring because it's really like cleared up. And the first time that I saw the ring, I was just jumping up and down, and people thought that I'm having like some crisis because you can really see the facility because it's close to the ground.
Oh, cool. I'm totally going to look out for that next time I fly home. Unfortunately, not able to go this summer, but I do that when I see telescopes out of airplane windows. You can sometimes pick them out if you know where to look on tops of mountains, but also I've seen radio telescopes from the air as well, which is pretty cool.
Yeah. And you can't do that thing in CERN, which is the other bigger facility, which is in Europe, because it is 100 meters underground. So, and you can imagine that to make a facility which is something like 26 miles long in circumference, you need to go underground because land is very expensive. So that's why it is primarily underground, so that it's nobody's territory. But obviously, that also requires large international collaboration.
Very good. So Charles, I wasn't keeping totally my eye on the time. How are we doing for time? Is it time for Sevil to take over and ask you some questions?
You can switch over at like 7:01 or 7:02 if you have another question.
Okay.
Otherwise, I can take it.
So I do. I have one more question actually that I'd like to ask. And so one of the fun things about writing this book, as I mentioned, was that we each wrote different articles in it. And so we got to write some articles, but we also got to read some articles. So I got to read all of the articles that Charles and Sevil wrote. And so I'm curious to know which was Sevil's favorite article to write.
I think the missing mass.
Oh, yeah?
The reason for this is, I define myself as a high energy nuclear physicist. And sometimes there is competition between my particle physics colleagues and nuclear physics colleagues about the time in CERN. Mm-hmm. And so when particle physics colleagues discovered the Higgs, they decided that, hey, they find where the mass is. You can describe the missing puzzle by knowing that what causes this mass. However, if you look at the missing mass section, right, what you'll notice there is that most of the mass that we have comes actually not from the Higgs, which gives the mass for the subatomic particles, but from the quark and gluon interactions. So being able to write that thing, I really enjoyed it because, more than 90% of the mass that you observe for example, a proton, what gives the proton the mass fundamentally is from the quark gluon interactions rather than the Higgs boson itself.
Very cool. Mm-hmm. And in astronomy, we use missing mass sometimes to mean dark matter, not this kind of much more like philosophical, feels philosophical to me, this idea of what mass is. I remember a kid once asked me that, and I was like, it is just what it is. And so it's neat to think that there are scientists who are actually trying to work out what mass is. Yeah. What it is that gives objects mass and course, that's the Higgs boson. I'm not entirely sure I understand how that works, but
Higgs boson gives the mass for your fundamental particles, because the expectation is that they interact through, we call these things like fields, right? So it will interact through these fields, and that interaction will result to what makes an up quark or down quark the corresponding mass. But a proton, which is made up of an up and down quark, has a huge mass than what you can come up with the bare masses of the quarks themselves. And this huge mass really comes from quark interacting with another quark through the gluon interaction. So
very cool. Very nice. Anyway, I'll hand over to you to ask Charles some questions now.
Yeah. And Charles, I think yours. Okay, good. So I mean, we mentioned that you are a professor, but you also work in the museum.
Yes.
So I was just curious, actually, what you do in the museum, in general.
That's great. Well, before I became a professor, I was at the museum, and what we were doing at that time was putting together the Rose Center for Earth and Space, right? The Hayden Planetarium, which was one of the first major planetariums in the countries, built in the 1930s, and by the 1990s had become quite obsolete, although still a grand old Art Deco building. And when I arrived, it was after I'd finished my doctorate, and we had come here into the New York area. I was a postdoctoral scientist at Columbia. And at that time, David Helfand, a person who Karen knows well also, was the head of the Science Advisory Committee for the reconstruction of the Hayden Planetarium. And so at that point, the Hayden was already a hole in the ground. But they wanted somebody to help with the designs and the exhibitry to support the scientists, so that the combination of the people who built museums and the people who were doing the science could come together and create something that was really reflective of both, sort of at the cutting edge. So that finished around the year 2000, the construction. But then for the next 3 years before I became a professor, I wound up doing a lot of work with the public. When people came to visit the Rose Center, I would explain things to them. I wasn't a tour guide so much as I was actually teaching the tour guides what to say and how to do things, and what we meant by certain things. Because when we're in our ivory towers as academics, we sometimes forget what kinds of questions that normal people who are not as crazy as we are in the field are actually trying to say when they ask us a question. And so did that for several years, designed public programs, had people who were involved in that. And then in 2003, when I became a professor, I retained my associateship at the museum and at the planetarium, so I could continue to do those things. Nowadays, during the school year, I only go to the museum occasionally, but during the summertime, then there we have a research program that's funded by many different organizations, NASA, the National Science Foundation, and within the past few years, the Alfred P. Sloan Foundation also. And we brought undergraduate students, college students from all over the country and within the area in all different programs to come do research. And so we're there, we do science, we learn about public programs. I still do the occasional thing where I'm talking to people in the public and so on. And we occasionally talk about the exhibits and the really cool, even scientific research, as well as the outreach that we can do with the Hayden Planetarium Dome, which is now a full three-dimensional projection space. So it's that kind of thing, a mixture of sort of things. And then I sometimes miss actually contacting with the humans that visit the museum on a regular basis. But I still get to do that every once in a while. Last summer, there was a group of about 60 school kids, high school kids mostly, from China. And they were doing a grand tour of America. And so I was able to give them a tour. And of course, I had to do it in Chinese, which is my first language from a long time ago, but definitely not my language in terms of explaining scientific stuff and exhibits and so on. So we had a lot of fun, and they were very forgiving of my goofy errors, because when I was speaking at a 4th or 5th grade level in Mandarin Chinese, they laugh, and that's okay. We have a good time with that.
Yeah, I think, yeah, exactly. And I guess you got involved in this exhibit, right?
Yeah.
From large scale to all the way to the small scale of subatomic particles, which is
right.
Really this vast scale. And my kids really enjoy going through this paths.
Yeah.
Yeah.
I loved that particular one. That was so interesting. I tell this to a lot of people. when we built the thing, I was the person responsible for making the calculations and how big the models were. So for example, this Hayden Planetarium sphere is 87 feet across, right? 26 meters. So if that sphere were the size of a virus, then how big is the size of a hydrogen atom? And if, as a hydrogen atom is this big, how big is the size of the nucleus at the center? And I did all the mathematics and I understood what they were, but it was only when the things were constructed that I took a look and I realized, my gosh, those things are small, So it's that feeling, the visceral idea, wow, those are big, boy, those are small, that came alive in the exhibit, which was something I could not do when I'm just talking about it in class, because sure, we can do the calculations, but can you actually feel the difference? And those exhibits allowed us to do that. That was a really rewarding thing for me to do.
Yeah, I mean, I will encourage anybody who's here who has not seen that exhibit to go look at the exhibit once this pandemic is over, I guess, right? It's a beautiful, beautiful exhibit, I agree. Actually, when you invited me to join this effort, I really enjoyed it so much and I felt really honored for that invitation. But I never had a chance to ask you how you ended up getting involved at the first place.
Well, I was the second choice, actually, as it turns out. This happens a lot in the field. In fact, I'm second choice for a lot of things in life. And it turned out, it worked out okay for me. The Ivy Press folks, what they ordinarily do is they ask some sort of person to be what they call the contributing editor or the consulting editor. A person, usually a scientist, but not necessarily an expert in the field. And they gather people to write a book. And each of these 50 topics in their 30-second books are written typically by a different person. So a book might have 6 or 7 different contributors to it. And then they would not necessarily be scientists or collaborators in any field, and they would just have it. So they were asking me if like I might want to write some articles for a 30-second book. And I was like, yeah, sure. Then I got a call and said, our contributing editor dropped out. Would you like to be contributing editor? And so I was the second choice. And I was like, well, maybe. Because although I was happy to add individual, say, articles about things having to do with cosmology in the universe, I also felt not familiar, uncomfortable a little bit with the way that the structure of the books are, right? As you know, we scientists, we collaborate. We work together as a team. We don't say, oh, well, Sevil wrote that paragraph in the introduction, and then Charles wrote that paragraph in the data analysis, and Karen wrote that paragraph in the conclusions or something like that. We are as a team. And it's a much stronger way of producing a really high quality product because we all are learning from one another. We're not separated from one another in that way. So what I did was I told these folks, well, thank you very much for considering me, but as a scientist, you sure that I'm the right contributing editor for you? Because that's not how I normally write projects. And they went back and thought for a little while longer, I guess. And then their acquisitions editor came back to me and said, oh, yes, actually, we thought about it, and we'd like to do a book more like what you have in mind as a scientist being the contributing editor or the consulting editor. Would you like to do that? And I said, well, sure, but the first thing you have to do is not call me a consulting editor. You have to call me a co-author, right? And all the people that I'm going to ask are going to be people who have expertise in the field that can come forward and put together something, fill in the things that I don't know very well. And as a result, combine to create a single work with co-authors and so forth. And they thought about that a little longer and said, we'll give it a try, see how it goes. So in a sense, although we are part of a series, this book is its own unique creature. And I think for those of you in the audience who are thinking about writing a book someday, always realize that your voice as the author, or even as a contributing editor, is very, very important to the editors. A good press, a good editor will see the uniqueness that an author can add to a project or take a direction that has something unique and interesting. And I'm really glad that the folks at Ivy Press, who are just really talented and terrific, I think you agree that we worked with Stephanie Evans and a number of other people, tremendously talented people, the illustrator, Stephen Rawlings. These all really talented and knowledgeable. I learned a lot from them, and to some extent they learned something from me too. So that's kind of how it all worked out. Being the second choice sometimes is just enough. And I thought about, who would I want to be the ones who could carry the story forward in areas that I was not strong in. And you two came right to mind, and that's where we are, and that's how we got here.
Yeah, thanks for including, I guess, us. So I'm looking at the time. Shall we go to the next phase, or shall we, dive in more?
Okay, I'll tell you what. Yes. So people in the audience now, please go to your chat. It does look like that video-wise might not be as easy in terms of hand raising and so forth. But click on the chat button, which is on my screen right next to the participants button down at the bottom of the screen. So some of you might have a different location. And just click that chat button and just type your question in and then hit return. When you type your message here, type it and then press return, and it should pop up on our screen. You see that there are already some people who have put chat on here. And those of you who don't use chat or use Zoom very often will find it interesting that these kids today, they're chatting on the side while we're talking in the front. How dare they not pay attention, blah, blah, blah. No, but that's actually how life is these days. And it actually enriches the conversation, I find. It requires a little bit more of my brain to follow, but it's really nice to be able to have those things across. So yeah, so let's just take questions, and then as the questions, when there are pauses or proper places, we can ask each other some more questions and things as well. So go ahead. Let's go to this one. Eugene to everyone asks, do we have an update on the age of the universe? Are the various estimates getting closer to each other? I think, Karen, you probably have the best handle on what's going on there.
Yeah, so the age of the universe is reasonably well pinned down. What you might know a little bit about, Eugene, I wonder, is that there's a bit of disagreement going on right now in measurements of the expansion rate of the universe, so how quickly it's expanding. And that obviously, we sort of run the clock backward with the universe is expanding, so everything's moving away from each other, and we run the clock backwards to find sort of the 0 point when everything was all at the same place, and that's the age of the universe. So these different measurements of how fast the universe is expanding do relate to some disagreement over the age of the universe, and it's a puzzle, which is a really interesting place to be in science. But there's different groups that measure the expansion rate of the universe in slightly different ways, and these two different groups, they're both really sure that the systematics are in the other group, or the problems in the other group, and maybe now we're starting to wonder if maybe there isn't a problem, and actually there's something about the two different measurements that mean we should, no one knows what it is yet, but maybe this is pointing to some new physics that we don't understand yet. But it's a super interesting time to be in observational cosmology with this this disagreement. Every similar disagreement in the past has been solved by oops, we did a mistake, and figuring out what it was, and then it sort of moved forward. But as I said, these two different groups are both adamant that it must be the other group that's making the mistake. So
well, 13.7 plus or minus 0.2 billion years or so is sort of the consensus at the moment, I guess. But yeah. but the other folks think it's older, right?
I think that's right. Yeah.
Mm-hmm. Yeah, it's pretty amazing. And let me mention that the expansion rate of the universe debate, although it has gotten closer, used to be much wider, right? In fact, there's a group of the astronomers in the 80s and 90s, I guess. By the time the 80s and 90s showed up, there was half the astronomers in the universe believed a gentleman named Charles Liu was correct, and that the universe was expanding at half the rate.
Yeah,
that
it was a really big difference. And now, now they basically agree compared to that disagreement. But the error bars, the right. confidence in which they're measuring the expansion rate has improved so much that they're disagreeing with each other again. And my funny story is, one of the first papers I ever published, I actually published a measurement of a Hubble constant. This is the expansion rate of the universe. And it disagreed with one of the groups. And so this old gentleman emailed me and told me I must be wrong as a young graduate student.
But in the end, one of the people that first bridged the gap was John Hookra, who was one of your mentors at Harvard when you were there,
That's right? That's right.
So yes, it's a fun place how that all goes. Okay, so Jennifer Markham asks, the comet Neowise, have you seen it yet? Apparently it will be gone by mid-August. Seville, did you see it?
No, we have our, we are surrounded by trees, so unfortunately not yet, but yeah.
Karen,
Did you manage
anything out
to see
there
it?
in Philadelphia?
Oh, I did. Yeah, I did just about manage to see it. It's pretty challenging. Philadelphia is a big enough city to make the skies quite bright, so a bit of light pollution. But I was able to dig out my old binoculars and take my kids out to see it. And I even managed to get an app that was able to take a long exposure photograph on my phone and get a picture of it.
Oh, fantastic.
I've been feeling a bit cross with the press, talking about how you won't be able to see it again for another 8,000 years. And I just wanted to reassure everyone that maybe you can't see this comet, but there'll be another one along. And if you can pick out different comets in a lineup, I'll be impressed. So don't worry too much if you've missed this one, but look out for the next one. So yeah.
Going to this is a more Montclair local thing. If you go to Eagle Rock Reservation the next few days, you might be able to see it there. Yes, I know of a person who did go there. That was one of those 4:30 in the morning trips. This is while it was still in the morning. And also, I did go with Alan, our middle child, to the Presby Iris Gardens on the north side, not the closed part, but the upper slope part, and was able to see it one Sunday morning. Way long time ago. It was very lovely over the trees. Now it's in the
I've heard it's gotten quite faint, so it's quite challenging now. So
it's getting a little harder.
It was already pretty hard when I saw it a couple weeks ago. So,
but you said binoculars was good, right?
We could see it with binoculars. We had to get the street lights in the shade of a tree, but yeah, we were able to find it.
Sounds good. All right, good luck, Jennifer. Hopefully it'll work out well. Okay, let me slide back a little bit. From the Saraisky family to everyone, can you talk a little bit about being women in science? I leave it to the two of you for that.
Do you want to go ahead, Karen? Or?
No, you go first, Sevil.
So, to be honest, I did not know that there is a, woman in a science concept. I guess this is one of these differences between, education back in Turkey versus back, here in US. When I came to, US as an undergraduate student to UC Berkeley, people were telling me, oh, you're a female. It must be hard. I'm like, what? What do you mean that it must be hard? Somehow it's a cultural difference, I guess, between how US looks at what a scientist should look like versus what a scientist should look like in other countries, other cultures. So for me, it was nothing but just my interests that made me come into sciences. There were times that I found myself a little bit lonely, and I don't like being lonely. I don't want to be, the only person in many conferences or other things. It just gets better. I think with time, things are definitely different than 20 years ago than now in terms of the numbers. It is still not optimum, thinking that we all start with 50-50. And if it works with other cultures that, we can continue having equal number of female and male scientists, it should also happen in US. US is not different than other countries in that sense, right? I think we have even the best writing here. So, there are difficulties, especially if I find myself alone, but you look at this crowd now, right? We are 3 people in here, 2 are female and 1. So Charles should feel bad about himself for being the only one, I guess, in here. But yeah, it's different, but I think it's getting better with time, let's say that way.
I think culturally the UK is quite similar to the US in this aspect. So it's very unusual, certainly 20 years ago, it was very unusual for women particularly to do physics. In fact, actually, we talk about women in science being an issue. It's really mostly women in the physical sciences. So biological sciences have mostly equalized. That's not entirely true, but the biggest issues are in physics. I, like Sevil, I didn't really worry about it. I just really liked doing physics. I really liked astro, and I was like, it doesn't really matter. I think the point where I started noticing some issues were when I had children, and I don't know if that is related to having had children or if it was my age or career stage. But at that point, you know, I found a few people being like, okay, when are you going to quit and give up this crazy career? Even from my family, some people have said that to me, which is not particularly supportive. I mean, I think my family didn't realize that they weren't being supportive, but I've definitely heard that. And just one last thing on this. It's been lovely. I moved to Haverford 3 years ago now, and the Haverford Physics Department, Physics and Astronomy Department, we have 6 tenure line professors, 3 of whom are women. And just to be in a community where it's equal, and it's not, it ends up, I don't think I had realized how much I was feeling it, that I was in a department that was basically all men before this. And it shouldn't matter, but it did a little bit. And so it's been really nice to be at Haverford where we're just all in it together because we're a balanced group of people. So
Oh, that's great. Let me follow up a little bit on this question, if that's okay. You know, I think of more, not just about the number of women in science or in astronomy or anywhere, but the quality of life or quality of professional experience that women have in the sciences, right? I mean, right now, let's just think, for example, we're here on this Zoom call, right? Not in the Montclair Public Library in the beautiful auditorium there, because in March, our talk was canceled because of the pandemic. And now we're doing this, which is lovely, but it's different. And it has affected people very differently. You know, do you feel that this kind of has highlighted some of the differences and the challenges that you have to face compared to, say, what I have to face? I mean, I see some of this stuff right away, and I see a lot of the news and my colleagues and so forth. But how has that been like, trying to do your lives now compared to even just a few months ago when it was already interesting and challenging enough?
So I can directly answer something in here. As we discussed before, I work with international collaborations. So that means that I'm on phone meetings every day in all these random times, even before pandemic. So I've been used to working remotely with people, all over the world. So in that sense, actually, we didn't change anything for me. Yes, I can't send my kids to daycare or school, or they're out of the house, right? So there is that difficulty. But in terms of like scientific, production, right? The things have been actually relatively easier, I think, for my job as a scientist, as a professor, than probably many people who are struggling right now due to pandemic. So there are definitely benefits, right? For having
absolutely.
Yeah.
I've definitely, I mean, I've missed the trips this summer. Normally this summertime we take trips for research conferences. I was going to be going to the UK, and I should have been in New York for a week, and all of that just happened over Zoom. And there are downsides to that for sure. I miss my colleagues, but also, it's convenient. When we're done with this, instead of having to drive 2 hours back to Philadelphia, I'm just going to go upstairs and spend some time with my kids. So it's very efficient in some ways, which is, that's great. There are challenges. There's clear statistics that women are preferentially taking on the additional childcare load because children are not able to go to school. In my family, I haven't felt that. I have a very supportive husband, and my children are a little older, so they just kind of do their own thing. They're watching too much. They're playing too much Minecraft, that's for sure. Yeah. But anyway, so I don't know. I hope there's some things that we learn from this experience of all working remotely that we take with us in terms of the benefit of facilitating people's remote access to meetings. I think some of that will help women preferentially. I mean, obviously this is all but there's some challenges, and the lack of understanding that childcare is necessary that I think we see from some of the people in power in many countries, not just in the US, is definitely hurting women.
That's too bad.
That's going to be a challenge.
Well, kudos to your spouses, and kudos to Minecraft. My youngest would certainly dispute your statement. There's no such thing as too much Minecraft. Maybe some of the people in the audience feel the same way. I don't know. Well, too much of anything might be too much of anything. Uh, that sounds like a quote, right? Too much of a good
There's
thing.
a great question in the chat, Charles. I like this one. What space movie has the most accurate physics? And I wonder if we could share our favorite space movies. That's a good one. Do you have one?
Apollo 13.
Yeah, that's a good one.
But in terms of science fiction, they all suck. But all in a good way, because I don't mind if it's wrong. I grumble about it afterwards. My family's always like,
fun.
"Stop it! Don't ruin it." It's like, no, but that's impossible, you know. But the sci-fi movies, none of them are really great. And as long as they are self-consistent, as long as everyone has to follow the same rules of warp drive, or the same rules of lightsabers or whatever, okay, fine. When things are inconsistent are things when I get a little concerned. I really don't have one particular famous one, favorite one. Do you two?
I mean, I only remember the really bad ones rather than the good ones. So, like, I remember Gravity being terrible with conservation of angular momentum. And I remember that specifically because then I was discussing that with my students, which were taking this intro level classical mechanics. So we were like evaluating what went wrong in that movie. But yeah.
Sandra Bullock and George Clooney. Oh my gosh.
Yeah.
Sandra Bullock was great, but the thing that bugged me about that was that she cried. She was a well-trained astronaut. She would not be panicking and crying in space. She would have been on it, because those astronauts are all on it. And just because she was female, why she had to cry in the movie, that bothered me more than anything else in that movie.
Yeah, anyway, I have another crying movie, which is this Angels and Demons, the movie, which is about actual Large Hadron Collider.
That's right. It's like antimatter to destroy the Vatican or something, right? With Tom Hanks.
But, you know, they have this little container that they are supposed to be trapping antimatter, which actually, to be honest, there are currently experiments that are happening right now to produce, for example, anti-hydrogen, and they are successfully even combining the hydrogen atom, which is an anti-version, which is the anti-proton, together with a positron, which is the anti of the electron. And then they study, for example, how it behaves in comparison to a hydrogen, and they are actually in the similar energy level. So there is some accuracy of that movie, but again, the main scientist was a very nice female scientist, but she couldn't know how to change the batteries of this instrument, which, you know, by the time that you have a scientist, you know, doing things at that level, should be able to switch a battery of an equipment. So there are many inconsistencies, right?
Frustrating, unbelievable. Okay, well, more questions are coming in, which is great. I think that's wonderful. Let's go up to toward the top again. I think Diego asks, why is there any universe anyway? What made it wake up? Karen?
Oh, right, great. Yeah. So my answer to this is that the physics that we understand just stops working when you get too close to the beginning. And so particularly, you know, the physics that Sevil and her colleagues can understand can take us back to very, very, very tiny fraction of a second after the Big Bang, after the beginning of the universe. But the shortest time that we're allowed to understand in the way we currently understand physics is called the Planck time, which I forget the actual number. Maybe Charles or Sevil has the number on the top of their head.
3 seconds.
Yeah. It's a very, very tiny time.
43
of them, right? Yeah. But before that, you know, we just, you know, we call it a singularity, and that's what we say is in the middle of a black hole as well. And it's really just a name for a place in time or in space where we can't explain it with physics. And so, you know, what made things start is not something we can answer with physics, which it gives you some space for some metaphysics. And I think Charles enjoys thinking about metaphysics. So maybe at this point, I'll pass over to Charles.
Fine. We have a problem in physics because we do want to make ideas that we can test, right? If you just have a theory and just say it is so, but you can't test it or falsify it or confirm it, then it is no more or less valid a theory than any other attractive idea that we like to believe. So unfortunately, what made the universe come into existence remains out of the reach of confirmation or testability, right? The latest idea is that if we decide that the universe is just a subset of a larger multiverse, there are physicists, for example, Lisa Randall at Harvard, who suggest that there is maybe a 5-dimensional membrane in the 11-dimensional supersymmetric bulk of the multiverse. And if another membrane touches this membrane at that location, much as 2 3-dimensional soap bubbles can touch and create a 2-dimensional film in between, 2 5-dimensional membranes can touch and create a 4-dimensional space-time. And our universe is a 4-dimensional space-time. And that touching is the creation of the universe moment that causes the universe to exist and so forth. Now, that's a very attractive idea, but first of all, how are we gonna ever confirm it or deny it, right? We have to find the rest of these membranes. How are we gonna do that? I don't know. Furthermore, where'd the membranes come from? You wind up with a new question that you keep going further and further back, and at some point it becomes the parable of turtles all the way down, right? What's holding up the earth? Well, there's just a turtle and a bigger turtle and a bigger turtle and so on. So at the moment, the answer is what made it tick? Still not sure, but at least we can get to how it ticked, starting from the first tick, which is 10 to the minus 43 second after. I don't know, Sevil, do you feel like quantum gravity or other sort of very sophisticated particle physics hypotheses and theories get us any closer to the origin of the universe than we astronomers can get there?
I guess it's going to end up being in the particle/nuclear physics territory, right, at the end, because even with observations, the length scales of you measure photons is already existing something like 400,000 years later after the Big Bang, right? So experimentally/observationally, we are limited up until, the photon is free to escape. And the rest is actually what we put it in, what we learn from what we have right now, and then try to extrapolate that knowledge back to the beginning. I mean, as you said, right, theory is just a theory until verified by an experiment. And as an experimental physicist, I use that quite often to say, these theorists, they don't really know what they're doing, because here's our data which verifies that their theories are incorrect. I mean, we have to, I think, a little bit wait and see what comes up next. And previous, explanations of things ended up being wrong as we continue, for example, taking more data, even like, planetary motions, right? How whether we are in the center of the universe versus we are actually rotating around the sun. There are ways to explain things in a different way, but more data, more experimental results will actually hopefully, help us to find more.
Great. This follows up very nicely this question from JP. I'll read it out, even though it's a little long. It's no problem. In my limited understanding, each discovery of smaller and smaller particles, each thought to be fundamental, seems to eventually reveal that the particle actually consists of mostly space. Might that happen with the Higgs boson? Is it conceivable that science will eventually conclude that the true fundament of the universe is nothingness, or space, or energy, or consciousness? Thank you all for this fun event. I think that feels like 2 questions. So let's go with the Higgs boson part first, Sevil, and then Karen, we can talk about the science concluding the true fundament.
Yeah, so Higgs boson is a special subparticle. And before maybe we go on to the special subparticle, so I guess Charles mentioned this a little bit, right? So if you go to, for example, in the level of quarks, which we think now that are fundamental, there are these theories called string theories, which describes these quarks in a way where an up quark or a down quark is an up quark or a down quark, because these are like little strings vibrating, and the energy level in these vibrations will be identified as an up quark depending on the energy that it has versus, the down quark, the energy that it has, right? They have different vibrational states. What is beyond the string theory? I mean, if this is indeed true that these subatomic particles, these fundamental particles, are just purely made up of strings, it can be like little loops, or it can be open depending on how they tie into the matter that we study, we can get some information out of this. So we have different particle species, right? We have bosons and then we have fermions. So the difference between bosons and fermions is, for example, how particles occupy space. Bosons are, I tell my students in a way where they can think of, if a particle is a boson, it can all sit in the same chair, 100 of them, 10 of them, millions of them. But if it's a fermion, every of the particles is an individual, i.e. they want their own chair. So different particles behave differently depending on their internal intrinsic properties. So even in the level of, for example, I gave the example of quarks, and I said protons are made up of 3 quarks and neutrons are made up of 3 quarks, but electron is a different species. And we call them leptons. So we have different species of particles, and how these particles came up to be might be possibly explained by this string theory. But we come into this level of experimentally verifying whether this string theory is indeed true. And so in my experiments, which is doing, for example, high energy, heavy ion collisions, that means, I take, for example, a gold ion, I strip all of its electrons, I just look at the seed, i.e. the nuclei, which is made up of protons and neutrons. And if I take this and collide with another gold ion, which is again the heart of the atom, we create this thing called, quark-gluon plasma, which we mentioned earlier. And what we learned is that the way that this quark-gluon plasma behaves ended up being in the limits of what, for example, string theory predicts for the most viscous liquid that we can reach. So there was some excitement about maybe heavy ion physicists can verify, the string theory, but we are just in the beginning of testing these types of things, because we are going to very small scale physics, and there's a limitation in the large scale and the small scale what we can really measure. Yeah, and then what was the other? I guess maybe I take care.
JP's follow-up is what's vibrating when you talk about a string? Is a string actually a particle with measurable mass?
I mean, you can think of it as like an energy, right? Visualization-wise, you can think of it as an energy that carries over. So we don't really know, right, what it is. It is just that its oscillations is causing us to have a material. So even, for example, I go back to E is equal to mc squared example. When I try to pull a quark out of my proton, a quark and anti-quark pair pops up. So as we call vacuum is not actually vacuum, it's not empty. We call it vacuum because things are not necessarily materialized. But if you can put enough energy to the system, then you can actually materialize particles coming out of this vacuum. And I guess the best example is I have been listening The Elegant Universe by Brian Greene. Brian Greene has these really nice visualizations for how it looks like in the small scale versus the large scale. The things in the vacuum level is actually really fluctuations of particles. And for them to be really, to be realized, to pop up from this sort of vacuum-like thing, which is like boiling, you can think of it as a boiling, things are very crazy, fluctuating up and down. For it to materialize so that we can actually hold it as a particle, I mean, we never always hold it, but you know what I mean, so that it can form a pencil, right? It needs to have specific energy. So that energy will make it a matter.
Wow, complicated but fun stuff to think about. Okay, Karen, your turn. Is the ultimate essence of space essentially nothing?
Well, Sevil mentioned the sort of the vacuum energy and the energy of the vacuum. And one thing astronomers have discovered in, I guess, the last 10 years now is that the expansion, we mentioned that the universe is expanding. Maybe you've heard of this maybe. But one big surprise in the 90s was the measurement that this expansion actually is accelerating. So it's faster today than it was. If you look in astronomy, we can kind of look back in time, right? If we look very far away, we look back in time, we can measure the expansion rate very, very far away, and we discover it was less than it is now. And that's contrary to any physics that kind of makes sense. Gravity is always attractive. So you would expect that an expanding universe would be slowing down, right? Because the gravity is always attractive. But in the 90s, astronomers measured that it's actually accelerating. And so this was, I remember in the 90s, I was in high school actually, and I read about it in a popular science thing, and it was talked about like anti-gravity. There's this like this mysterious substance that's pushing the universe apart. We call this dark energy. And one of the consequences of the accelerated expansion of the universe, if this dark energy is what we think it is, it's always constant, it's always there, it's somehow related to vacuum energy, although it's many, many orders of magnitude bigger than the predictions, I believe, for the vacuum energy that come from our particle physics colleagues. But anyway, as this expansion continues, this dark energy will be everything. Everything else will become negligible relative to dark energy. We'll enter the dark energy dominated era of the universe. So I guess in the very far future, our prediction is that yes, the universe will be nothing.
Oh, yeah. And
Yeah.
I'll jump in on the metaphysical aspect of that, right? Because vacuum is actually not nothing. Right? It is no thing, but it is its own thing. In the same way that when Albert Einstein first came up with the general theory of relativity and explained that space was not just emptiness, but it's actually its own structure. It's like a gel or a material, a matrix within which things are populating it, right? And pieces are part of it. So in that same way, we have to open up our ideas and thought about what nothing is if dark energy truly is a something, but it just happens to not have structure or thing that we're familiar with the way that we have now. And this JP mentions consciousness, you know, with the big exclamation point and a question mark. That's actually a neat idea, again, a philosophical idea that has not been proven in any way, confirmed scientifically. And some people refer to that, this word is used in different contexts, but there's this term called biocentrism. The idea is that the universe consists of things like thoughts, right? Even though thoughts are only what float around inside our brains and what we can experience back and forth, it is part of all that exists, doesn't it? So in a sense, a thought or an action or a philosophy or an experience or an observation is just as real a thing in the universe as a star or a galaxy or a planet or a person. And so is it true that the universe that we observe or understand exists only because we do? If we biological creatures did not exist, if we not being these sort of perfect examples of local violation of the second law of thermodynamics or something like that, does that mean that the rest of the universe wouldn't be that way either? So it's a strange idea. It's almost like an extension of the old question: if a tree falls in the woods and no one hears it, does it make a sound, right? If the universe exists, or if the universe is doing its thing and there are no people around to observe it, does it actually exist? I'm guessing that if extraterrestrial life is commonplace, it doesn't matter whether I exist or not. But does it matter if anybody exists? But if anybody exists, then, well, that's the universe to begin with. We're already there. So that's the fun, humorous, fun part of the metaphysical question of, are we really here? Is the universe really made of nothing? All that stuff is kind of fun to think about. But don't want to get too deeply into that part. Speaking of other creatures, okay, let's go to Tom. Without reading the whole question, let's just jump to the end. Do you think that a first contact scenario with aliens would be more like a friendly one, like Spielberg doing E.T., or a vicious one like War of the Worlds with Herbert George Wells, or Orson Welles' War of the Worlds, right? Should we advertise our existence to the cosmos, or on the side of caution and hide ourselves? What do you think?
I think it's too late to make the decision at some level. So we have been transmitting ourselves to the cosmos, I believe, sometime in the late 1930s were the first radio and TV signals that were strong enough to make it substantially far away from the planet. So there is a bubble around us about 70, 80 light years in diameter, in radius rather, in which if aliens did exist, intelligent aliens did exist, they would know that we were here. I don't know, Tom. I do worry the history of humanity is full of civilizations meeting and it not going at all well. You want to be on the side of the more advanced civilization. And if you look at the timescales involved, you know, there's only been life on Earth for 1 billion years. Humanity's only been around for a few thousand years. The galaxy has been around for, you know, well, a long time, 10 billion years, I would say. And so the odds are that civilizations that are out there are more advanced than us, and we will not do well if they find us. But I think the cat is out of the bag, as they say. I think we are communicating that we're here, and so I guess we have to hope that alien species are not like humans and don't run around and colonize everything and kill every bit of the indigenous population that they find, and so on and so forth. But the history of humanity does not give me hope in that.
Sevil?
I mean, I don't have that much to add, but just to follow up on that, if they are really evolved, probably they are evolved in a way that they don't want to abuse us, right? And probably if they are evolved, they are probably watching us saying, oh my gosh, this is such a low level, you know, civilization. So yeah, I don't know. I mean, this is really, you know, beyond our experimental observation, right? We don't really know. We don't know even how we get the contact. So
right.
I wouldn't really worry for our generation yet, I think, for being in contact with any aliens or any.
Right. I mean, we human beings have created sort of fictional things to protect ourselves. For example, in Star Trek, we imagine that more advanced civilizations haven't killed us because they believe that it is a moral imperative not to interfere with lesser civilizations, right? But really, the better way to think about it might be that with all the billions of years of difference in evolution, we might be perceived by some advanced alien civilization or organism as something akin to an anthill, right? Or a termite mound or something, somewhere in the middle of nowhere. So as long as we're doing our thing in our little corner of the galaxy, a little ball of mud going around, a little ball of gas, right? That is the Earth and the sun. They're going to leave us alone. But the moment they want to build a house or that they want to make a highway through this area, whatever
the Vogon constructor fleet will come and
that's right. Those will be gone, right? Yeah. And I think Douglas Adams in The Hitchhiker's Guide to the Galaxy actually got it right. Yeah. You're like, you just, why didn't you go to Alpha Centauri and take a look at the paperwork? You know?
I mean, come on, it was on display. Yeah.
Right. So
to be a bit reassuring, though, maybe we should talk about the scale of space. And I mean, you kind of hinted on it when we talked about the scale model in the Rose Center. But
yeah, that's true.
I mean, space it's really, really big, to quote Douglas Adams, I believe, again. And you know, that probably means the likelihood of there being some other life out there is pretty high, but it also means that the likelihood of it visiting us is very, very low. As far as we understand it in physics, you know, all this stuff about warp drive and faster than light travel, none of it is possible. And so, you know, the nearest star would take decades really to get at any speed that seems feasible. And so, you know, the idea of sort of Star Wars or Star Trek like going all around the galaxy is just implausible, and so that kind of is likely to keep us fairly safe.
I agree.
Yeah.
That might be the safest protection, is just being really, really small in something really, really big, right?
Yeah.
Okay, so let's jump back. I think we have time for a few more questions. Jumping back to just a tongue-in-cheek question, but I think it's worth answering. I'll give this to Karen. Terry Schulman asks, what's the deal with Pluto?
It's a good question. Pluto's doing everything that it always ever did. It doesn't care what we classify it as. It's just out there in the outer solar system doing its thing. But we now know that it is not unusual at its orbit. So there's lots of things about the size of Pluto that orbit in a similar orbit to Pluto. And so it's just not a major planet. It's not a planet that's big enough to sort of dominate its orbit. And so it got reclassified as a dwarf planet. But it's just doing the same thing it always did.
Okay. What about traveling through wormholes? is what Jasmine asks. Hey, Sevil, I'm going to ask you this because, look, in astronomy, wormhole, nah. But is it possible on some subatomic level, like you tunnel from one place to another when you're not supposed to and wind up somewhere else where you didn't think so? This issue of like quantum entanglement being a teleportation device. Can you talk about that a little bit and see, is there any possibility at all?
I mean, there's always a possibility, right? That's what quantum mechanics teaches us. But I guess like the wormhole as a definition is something that is, so what we understand. So we normally live in this, X, Y, Z, our land, and then there's this height, right? We can take airplanes, so we can go up, and then we walk around in this surface. And that's normally our sort of space. And what we learn is that that space and what we measure with time is actually interconnected. So many of the physics phenomena that we sort of study, even in the small scale and large scale, you have to think about it both as, the land that we walk, the height, and also the time together. So wormhole, I guess, in these science fiction movies and so on, means things which this space and time that we have has these little loops. So the simplest example is, you can take a piece of paper, right? If you're an ant walking on this piece of paper, you can sort of walk around this paper to come from this point to this point. But instead, if you just have a little opening where, a point in here and a point in here can connect, right? You can actually make the distance much shorter. That we really don't know, right? If we can make these little sort of loops of space-time where the space and time curled in a way where you can sort of create a wormhole. I think that's the science fiction direction, right? How the space-time is sort of curled and whether it is possible, we don't know. What I think Charles was asking is, do you know that so in quantum mechanics, we know that there's a probability of, let's say I trapped an electron in a proton, right? And there's a probability of finding that proton out of the atom for a, given probability. And quantum mechanics allows us that. I guess this is the direction that you were going to, Charles. Yeah, so in that sense, I mean, I have not looked into the calculations of what is the possibility for doing things like that, but in the small scales, subatomic scales, it is possible. And that's, I guess, how you transform even the information. But the limitation of this transformation of knowledge is always within the speed of light c, right? Information transfer. So you cannot be faster than that. So there are limitations in that, level too.
Life goes on.
Life goes on. Yeah, this is sort of a
wormholes are great ideas if you want to tell a story or a space opera. You have to get from one place to another fast, but the actual existence of them pretty challenging. And we haven't found them. If they existed in nature, we'd find them by now. We'd know they're there already. We just don't have them. So that's too bad. Alas. Okay, so I think we can wrap up. And Maurice, I want to hand it back to you in a moment, but can I ask Karen and Sevil to make one final, just a parting thought, maybe something in the book that you wrote that we haven't talked about yet that you might want people to sort of think about as they head off into the evening and wonder about the universe as it goes on? Give it a second and see what you think. I'll give one right now while Karen and Sevil are thinking, and then I'll let them sort of wrap up and then hand it off to Maurice. I want people to know that the universe is more than just stars and planets and galaxies and asteroids and things like that. It literally is all of matter, space, time, energy, thought, all of that exists. And in that grand view of what the universe is, the idea of cosmology or metaphysics or things like that transcends the objects inside it. Now, obviously, I study the objects inside it, so it's fun for me to do that, and I would never make light of those things. But when we think more grandly we realize that everything that we do has value and substance. And so if we can think about that in this big overarching way, I think we find neat insights in the realization of interconnectedness for everything: science, arts, humanities, astronomy, biology, chemistry, physics, all of it. And I just love thinking about that because it's really a lot of fun to be able to feel like you're not just one little tiny corner of the universe, but the whole thing as a whole. That's sort of my thought. Sevil, you have a thought?
I mean, yeah, again, maybe following up your lead, right? I study some very small particles, small objects that we don't really see. So there are many things that we don't see, and then there are things that we can see. We can look at the vast sky, you see all these stars, right? At the end, we can describe a lot of the things that are happening in the large scale with the things that are happening in the small scale, right? Things need to be formed in the smallest level. So nature is really actually very simple, in the sense that if somebody is explaining you things in a very complicated way, that means that we really don't know what we are talking about. So I think and physicists are sort of still struggling for these big questions, right? Try to find simple explanations, because the simple explanation must be the true one. But again, from small scale to large scale, everything sort of can be described with the physics that we know of in our universe. If you go to another universe, which is possibly parallel to this, things might be different. But as far as we can verify, right, we are doing the things in one, particular way of physics to describe the smallest to the largest.
Yeah, it's a beautiful thought, that sort of interconnectedness of everything. And it's a real principle of cosmology, right? The idea that the physics in our universe is the same everywhere. And I wanted to come back to sort of Charles's thought about, how we're all connected, and just leave everyone with the thought that you literally were all in the same point in the Big Bang. And just make sure that you go away understanding that you were in the Big Bang. The material that makes you was in the Big Bang. The space in your living room was in the Big Bang. So often there's this misconception that the Big Bang is a point in space and an explosion happened and that all moved out into the space. But of course, the Big Bang was the creation of that space-time. So everything in the universe was in the same place when the Big Bang happened. So think of it as a point in time, not a point in space. And just go away knowing, you literally were connected with everything at that time, because everything was at the same point in space at that time.
Mm-hmm.
Yay! Okay, Maurice, it's up to you now.
Yeah, we're gonna call it a night. Thank everyone for coming out. Thank you, Karen, Sevil, and Charles. Again, thank you everyone for being flexible. Anyone else, people have lost, had some power outages tonight, and hope you guys are all back up, in the coming days. But this was a wonderful discussion, wonderful chat all around. And this is our last lecture program for the summer. So wish everyone have a good summer, and we'll see most of you again in the fall. Until then, be well, be safe, and thank you again to our three panelists. Take care, everyone. Have a good night.
Thank you, Maurice.
Bye.
Bye-bye, everyone.
Oh, Tom, sorry I didn't get to answer your last question. That's okay. We'll talk about it sometime. Spiritual beliefs, contradictory, complementary, or neutral to science? I say they are neutral. I don't know. Sevil, Karen?
I know a lot of scientists who have a lot of different beliefs, so they seem pretty neutral to me.
Yeah.
Yeah.
And Sevil seems to be nodding too?
Yeah.
Yeah, I think that's right. Remember, religion was created by humans who are part of the universe. So why not have spirituality and religion and things like that be part of the universe? Does any particular one have to transcend the other? Is it positive, negative? It's just a thing. It's part of the universe, like all of us, like we were in the Big Bang at one time. Right, Karen?
That's right.
All right, Sevil, thank you so much. Maurice, thank you again. Okay.
You got Charles. Thank you, Karen. Thanks,
All right.
Sevil.
Bye,
Thanks,
everybody.
all.
Thank you so much. Bye.
Yes, you can find their books online, so I should say that. You can find their books on Amazon, correct, Charles?
Yes.
Universe.
Yes, that's right. And someday in your bookstores. Okay.
Take care, everyone.
Bye again, everybody. Thank you.